it actually even started. Okay.
Linguists are increasingly reporting on data sets and statistical analyses in their articles. But what happens to the data and code after the articles are published? And what if someone wants to access that data?
Yeah?
Hi, I'm Scotty, junior linguist, and I'm writing a dissertation on nominalization in Klingon. I read your article with the logistic regression analysis of Quenya, and I really thought it'd be great to compare your data with mine, and I wondered if I could get a copy of your data and code.
That study was done several years ago. Let me go take a look.
Okay, thanks.
Nominalization. Quenya. What year was that?
Keeping your data files on a local computer or server is a bit like keeping your money under your mattress.
Transitivity? No. Adjectives? No. Conjunctions? No. Ethical data? Definitely not ethical. Capitalization? No. Reduplication? No. Stress on borrowed nouns? Definitely lots of stress. This might be it. I can't really read this one anymore. And where's the code for the logistic regression? Oh, shit. Listen, I think I need some more time to locate that data and code.
Locate it? You mean you don't have it? Is it lost?
No, it's not lost. I just need to organize it, make sure it's readable, you know.
Okay, but it's kind of a famous study, and I really need it for my dissertation.
Well, I'll do my best, but I can't promise anything.
Promise anything? You can't promise anything? It was funded by the Hypercorrect Linguistic Science Foundation. Doesn't that mean we're supposed to share the data?
Just give me a little more time, like a few weeks.
Weeks? I can't wait that long. What about my dissertation?
No. Don't call me. I'll call you.
No.
Good morning.
Good morning.
How can I help you?
I'm Scotty, junior linguist, and I'm doing my dissertation on nominalization in Klingon. I was wondering if you had any data sets that were similar to mine that I could use in a logistic regression analysis.
Okay, let's see. So now I have you logged into trolling, and we have nominalization, we have nouns, we have logistic regression. Do you have any other keywords?
Yeah, how about constructed languages?
Okay. Yeah, you hit the jackpot. We actually have 22 studies that match your query.
Fantastic. Can I have them now?
Just wait a second to beam them up, Scotty. So here you go.
Oh, now that is substantive. I'll be able to get my dissertation started and maybe even get some articles written on the side. Thank you.
Just before you go, when you're ready to submit your own dissertation, remember to come back to trolling and deposit your own data, because that's the best way to get a return on your own investment.
I'll be back. You betcha. Thank you.
Bye.
Trolling is a bank where everyone gets richer. And who knows, maybe you can even earn interest. That is, in your research. Find trolling at opendata.uit.no.
So anyhow, I wanted to tell you a little bit about this resource that we've created at the University of Tromsø in order to promote the use of statistical analyses in linguistics. I'm sorry, I just got to close this one. And we call it trolling, and it's at this website that was just mentioned. And at this website, you can get access to all kinds of data that's been uploaded, and you can also upload your data there. So this is, everything here is free and open access. You don't need to even have a password in order to download data from this site. You do need a password in order to upload data to the site, and it is monitored. And we also made a series. I'm only going to give you a little bit of, show you a little bit of it. We made a series of instructional videos. I'll just begin and just show you a little bit of one of these, so that people could learn how to use it as well.
Once you have an account in Trolling, you can begin to archive your data. Creating a study in Trolling is a two-part process. First, you enter descriptive information about your study, and then you upload your data.
I'm actually going to jump ahead a little bit because there's a bunch of boring things about giving permission.
Acknowledge that you have read and accept the terms, and then click Continue. On this page, you enter descriptive information about your study. Red stars are for required fields. Green stars are for recommended fields.
Etc., etc. Basically, your grandmother could upload data to Trolling because it's all explained here in tremendous detail. And the idea is that this can be a resource where we can all learn from each other about the use of statistics in linguistics. So now I'm going to move into my presentation, and the idea of this presentation isn't really to explain everything about the use of statistics in linguistics, but just to give us a little bit of a taste for it. Let me just bring that up. So I'm going to start from here. Yeah. Okay. So there we go. So really quickly, I'm doing this from the perspective of cognitive linguistics, so I'm just going to give some basic facts there, and then we're going to go through some various uses of statistics. So cognitive linguistics makes a minimal assumption that language can be accounted for in terms of general cognitive strategies, and so there are many assumptions that it doesn't make for that reason. Very important for us today is that it's also usage-based. That generalizations emerge from language data, and also that meaning is central. But particularly the usage-based. So what is cognitive linguistics? It's a theoretical framework that attempts to explain linguistic phenomena from the perspective of general cognitive mechanisms. We expect meanings to be the motive for language, and that we expect to find linguistic categories based on prototypes with extensions via metaphor and metonymy, and that lexicon and grammar are continued and thus observe the same patterns. But most important for today is that we're going to focus on an empirical and statistical analysis of authentic language data, and I think this is important. This is very important to us because I think linguistics is a field that is still struggling to define even what data is and what is the data that counts. So it's, already taking a stand by deciding that we're going to look at language data from the perspective of what kind of authentic language people produce. So that's the perspective we're taking from here. Now, a couple of years ago, I did a little survey of the use of statistics in the journal that's called Cognitive Linguistics, and I just made a little graph. So each of this is 1 year of the journal. 1990 was the first year that the journal was published, and here is the percentage of articles for each year that contained some sort of a statistical study, reported on a statistical study. And in the year 2005, for the very first time, we crossed this 50% mark. And in the year 2008, we crossed it definitively, and I don't think we're ever really going to go back. I don't expect that we're going up to 100% either. I think there will always be a place for other kinds of studies, more theoretical essays and such. But I think that statistics has come to linguistics. It's here to stay, and that we all need to learn how to live with it. So approximately, at least for our journal, this happened around 2008 in a definitive way. There were historical reasons why this happened. I think this happened partly because our particular journal is focused on a very sort of data-friendly approach to language. So quantitative studies were always welcome. As you see, we always had quantitative studies, even in the beginning. And then also in the last decade or so, or 15 years, we've seen the advent of digital corpora, like, for example, the Russian National Corpus, and also there's become much more available statistical software for the analysis of all kinds of things, but including languages. And there's been some development of particular software for specifically for linguistics. And there's also been some progress in computational linguistics. So there are historical reasons for this as well. And what this means for the future is that we all need at least some passive statistical literacy, so we'll be able to make sense of statistical studies that are presented. And linguistics as a field is still really in the experimental stage of using statistics. Psychology and sociology and such are further along than we are. So we're really at the point of developing best practices for use of statistics and linguistics, and this is why I think something like trolling is particularly important, because if we can publicly archive data and statistical code, then we can learn from each other and establish best practices that will contribute to the advancement of our field. I'm going to look at just a few statistical methods and some examples of how I and other people have been using them recently. And there's plenty of room for experimentation here, so this is not intended to be definitive. And my idea here is really just to give people a taste of what are the kinds of questions I can ask and answer using statistics. So let's start with a very simple test. This is a chi-square test. And when you use a chi-square test, this is usually when you have a matrix that has two types of categories, and you've got to count for each cell in that matrix. And you want to figure out whether there's a relationship between those two types of categories. So an example of a question that I asked a few years ago is there a relation between S in the prefix S to mean do something once, as in sklupic, and the suffix nu, as in verbs that also mean to do something only once, like chikhnut, and the verb classes that they attach to in Russian. And so I collected some data, and we find, for example, verbs in the I class, like zivat, prefer nu, and verbs of the non-productive type, like lidizits, prefer also nu, and this is also true for verbs that have the original suffix in yats, which actually, for most of those verbs, because of subsequent sound changes, it's actually an ah. So this is not just swistates, but also chats, for example. These also seem to prefer nu. Then we also have verb classes that prefer s. So we have like the ovets class, like maladushstvovets, that prefers s, or grubits, the E class, prefers s, and also the yates type, so rabits. And this, because of phonological changes, also includes a lot of verbs in niches, for example, that refer to behaviors. So then I collected this data. These are just basically type frequencies, not token frequencies. It's something I did quite a while. And here you have like a visualization, and you can see that these are the ones that prefer nu, and these are the ones that prefer s. But there's overlap. It's not all one way or another. Here's the same data in a table, and so then we did this chi-square test, and how do I interpret this? Well, here I have my probability value, and this is the chance of getting such an unbalanced distribution, or one that is even more extreme if there really wasn't any relationship. And basically, this is 2 and 2 with 16 zeros to the left of it. So this is a very low number, basically the equivalent of 0 for our purposes. So that's the probability, and then you want to also look for an effect size here. And here we measured this with the Kramer's V. This ranges from 0 to 1, where for less than 0.1 would be a non-reportable effect. 0.1 would be a small effect, but a reportable one. 0.3 would be medium, and 0.5 would be large. And here we got something really large because we got 0.8. But there are things to be wary of with all statistical tests. With this particular test, chi-square assumes independence of observations. So this is kind of like, you can think of this as you don't want, if people are voting, you don't want one person to have more votes than the other person, right? So everybody should have only one vote. And it also requires at least 5 expected observations in each cell, which means that if you have large matrices, you can run into paucity of data problems in many cases. But we did find a relationship between those two affixes that mean do something once in Russian and the actual verb classes that they attach to. Here's another example, which was done together with Olga Lyshevskaya, where we were looking at the relationship between form and meaning for prefixes and meanings of verbs. So there are a lot of cases where you have an imperfective base verb and the prefix perfective has the same meaning. It's just the prefix partner word. So we have like посоветовать, сварить, написать, затвердить, прогреметь. But are these prefixes really empty, as is sometimes claimed? And what we did was we looked at 382 verbs that supposedly had so-called empty prefixes that also had unique semantic tags independently assigned in the Russian national corpus. And we again did a chi-square and Kramer's V, and a little bit later I'll also show you how we did the Fisher test on this. So here is the raw data that we got from this, and we did a chi-square on this. And here again, we find that the chance that that there's no relationship between the prefixes and the semantic classes is none. This is this computer's way of saying 0. And also we have a fairly large effect size, which wouldn't surprise you if you looked at this graph, because you can see that basically each prefix has its own semantic profile, and here you have those there again. So we were able to say, yeah, certainly there's something going on here, and more than that, what's going on here seems to be something has to do with the semantics. Here's another study also done with the same co-author. I have another picture. And we were looking at the grammatical profiles of verbs in Russian and looking at whether perfective verbs behave differently from imperfective verbs, and also whether it matters how what kind of morphological marking is used in order to distinguish between perfective and imperfective in a pair. So here we're looking at paired verbs, verbal pairs. And here is our raw data. So this means, for example, we had 1,330,000 non-past forms for imperfective verbs, but only 375,000 non-past forms for perfective verbs. This is exactly the same data visualized in a chart here. And we do a chi-square here. Now here we have a huge amount of data. This adds up to about 6 million forms because it's so much data. You basically overwhelm the chi-square. You always get this here. But the important thing is that the Kramer's V was also quite large. So we found that, yeah, perfective verbs behave differently from non-perfective verbs. So perfective verbs seem to prefer the past, whereas imperfective verbs prefer the non-past. Well, that wasn't a very amazing finding, not very surprising, but maybe kind of more interesting was to look at this data disaggregated according to how the perfective-imperfective pair was marked, whether it was marked by a prefix or by a suffix. So here's that same data, but disaggregated according to type of morphological marking. So we have what we call P partners, where the pair was marked by a prefix, and we have S partners, where it was marked by a suffix. And we have this distribution of data. Well, it's kind of hard to see in the table, but here I can show it to you in a pair of graphs that we made. And here you see the data for the imperfectives on top and the data for the perfectives on the bottom. And so the perfective partners, that's like pisats and pisats. And the imperfect and the suffix partners, that's like piri pisats, piri pisivits. So in a sense here, this top graph then is comparing, this is comparing like, this is comparing pisats with piri pisivits, if you will, and this would be comparing napisats with piri pisats. Yeah, those kinds of types, yeah? And what we see here as well, it looks like there's a little bit of a difference, and again, because we have so much data, we kind of overwhelm the chi-square test. But so it's statistically significant, but the effect size is an order of magnitude too small to be reportable. So basically, it doesn't matter whether you mark the verbal pair with a prefix or a suffix, the overall behavior is extremely similar. So that was another use of chi-square. There are other ways in which people have used chi-square. I think we'll go through this kind of fast. This is the English ditransitive, where you have some verbs that alternate that can take both constructions. So that's like tell, where you can both tell a story to Mary with the prepositional dative construction, or you can tell Mary a story with the ditransitive construction. And then there are verbs that supposedly only take the prepositional dative construction, although of course the picture looks a little more complicated when you look in a real corpus. And this is the kind of problem that has bothered generativists for a long time, is how do children actually learn the non-alternating verbs do not use the ditransitive construction, since there's no negative evidence. So, and there are two cognitive linguists who also looked at this and did some studies. One was Anatol Stefanovich, and he looked at 50 sentences per verb. And his factors were alternating versus non-alternating. He looked at a number of other factors, but he did not find significance here, and he did not find support for preemption. But then along came Adele Goldberg, and she said, well, I'm going to look at a lot more data, and I'm going to look straight at just the verb class as alternating versus non-alternating, and this construction issue here. One thing to notice is that there's a big difference in frequency for the alternating verbs as opposed to the non-alternating verbs. The alternating verbs are much more frequent. And what she showed was that you really could probably learn whether a verb was alternating or non-alternating as a child acquiring English, because the chances that you would get the prepositional dative with a verb that can take the other construction is extremely low, whereas the chance of seeing it for the non-alternating verbs is very high. So there is a lot of evidence for preemption. So she actually used, they both used the chi-square test for this. I think this is my last example for chi-square, was a study done by Falk and Gibbs on the use of English path word versus road. And they did both an experimental study on how people perceive path versus road, and then a corpus study on how those words are used metaphorically. And they also did a chi-square analysis of this. And basically, the idea here was that paths were understood to be something that involved, that were more difficult and not straight and involved barriers, whereas a road is something that facilitated moving forward very fast. And there was a relationship between the understanding of paths and roads and the metaphorical choices, where path was more appropriate for describing personal struggles in life, and road was more appropriate for straightforward progress toward a goal. And they showed the significance relationship here using the chi-square test. Okay, so let's say we've done our chi-square test. We have a matrix of values, and Peter has a question already.
May I interrupt you? Because what I very much like to take home from this is that in order to really get something convincing with a chi-square test, you have to apply Cramer's V as well.
Yes, I feel really strongly about
yeah.
that.
Could you probably not now but later say a bit more about Cramer's V? Because, for instance, well, lay people like me who do not use R because they are illiterate, you do not get a Cramer's V calculator, so to say, together with your chi-square calculator. And if it's kind of so important.
Yeah, it is
so
very important.
what's
There's a package in R called VCD, like Victor, Charlie, David. Yeah, there's a package in R called VCD, and I can show you code where it will directly produce with the chi-square test also the Cramer's V. But Cramer's V is actually easy to calculate. So, and the way you calculate it is you, hang on for a second. So, I'm trying to, if I memorize. So you take the square root of the, the square root of the total, of the chi-square value divided by the sum of all of the items in your table, how many items you have in your table, and so the sum of observations multiplied by the degrees of freedom. For many cases, if the degrees of freedom of the shortest side of the matrix, for many cases that's actually 1. So it's often just the chi-square value divided by the number of observations and the square root of that value. If you have a very large complex matrix, then you actually have to also multiply something in that denominator. But there is this VCD package, and if you write to me, I can also send you code. So there is
Laura, actually the formula is described in Wikipedia, so it's
it's described in Wikipedia.
Very easy to find.
Yeah, it's very easy to
Cramer's
find.
V.
But thank you for bringing that up. It's important to have the effect size because the chi-square test gets easily overwhelmed once you have like over 1,000 data points. It starts getting overwhelmed, and everything, no matter how flat your distribution is, every little bump becomes significant. So okay, so thank you, Peter. So then we go to the Fisher test. So we've got a matrix here, and we want to now figure out what are the hot spots in that matrix. What's really pushing things in one direction or another? And now we can use the Fisher test. And let's go back to that data that Olya and I looked at with this relationship between the semantic class of the verb and the choice of the prefix in Russian, and look at precisely which combinations are significant. So we had, for example, proa with sound and speech as in progrimiets. Look at that. That's probably really significant. How are we going to do that? So we're going to take a Fisher test value for that one cell. So that one cell was this one here. Yes, it's this 51. And the Fisher test basically compares that value with the values for the rows and the columns and the total. So it's basically what you're trying to do is figure out how surprised should I be that I got a value this extreme, or I could get a value this extreme or even more extreme, given how many items I have in a given row and in a given column in this table. Some caveats here is that the Fisher test is not designed to work well on large numbers and large differences. And we'll get back to that in a bit. So we can do this for this value. First we have to figure out what the expected value is, because we have to compare, we have to know whether it's larger or smaller. And we get the expected value by this formula, And here's one way to get that expected value. So the expected value was 18, the observed value was 51, so it was much greater. So we do, I won't go through this in much detail, but basically we find out that this was the probability that we would get 51 examples or more if the actual distribution was random. So this is telling us that the probability is basically 0. And so but that wasn't a very interesting example because, I mean, that was a really big outlier. But look at these. All of these values are 11. Is 11 really equal to 11 equal to 11? But what does the fact that, these rows and columns have different values overall, what does that do to these 11s? Are these 11s all 11? So then how do we figure that out? And even here we can't really see, I mean, so here are those 3 11s, but this doesn't really take into account, this takes into account only the relationship seen from the point of view of the prefixes, but not so much from the point of view of the overall distribution of the semantic classes. So here, once again, we look at our expected values. In this case, all of these expected values were bigger than 11. And so then we can look at the difference, and here you can see that the differences are quite different. But still, what does this mean when we can go and do a Fisher's test for all of these? Here they all are. And to make a long story short, what I find out is that this situation for poa with impact verbs like pakrits, that's very significant. There's a strong repulsion. Poa doesn't seem to like the impact verbs very much. But the situation with s and change of states, like in zgnit, that's kind of neutral. There's no strong attraction or repulsion there. But we have I'm sorry, that was not quite neutral. There's some repulsion there, but we have really neutral here with the behavior. This was the poa like palinitsa. So we have, this one was neutral, this one's small repulsion, and that's a fairly strong repulsion. So we can say that they really are different, and we can go through and measure all of these and figure out where we have attractions, where we have repulsions, and this has various implications for also how we would teach students who are learning which prefixes to put on what kinds of verbs. So here we find a strong repulsion, here we find something neutral, even though these are actually the same values. This is rounding here involved. And then here we get a moderate repulsion. So we get a little more information out of that from the Fisher test. That was one use of the Fisher test. Here's another use of the Fisher test that's actually quite controversial, and this remains controversial to this day. I'll tell you a little bit more about this. So even though this article came out 12 years ago, and this article was very important for cognitive linguists because it was sort of a watershed moment, even though Dirk Gerards had been doing statistical studies for quite a while in cognitive linguistics, this was really the article that brought statistical studies more to our attention. And here, Stefanovic and Greece were looking at what they call collostructions. So this is when you take a construction and then you look at the relationship of lexemes that can go into that construction. And although this article was published 12 years ago, there was since a critique by Schmidt and Kuchenhoff that was published 2 years ago, and there's now coming out a rebuttal and a reply also to that rebuttal in a future issue of the journal. We're still working on that issue because this particular use of Fisher test is controversial. So here's what the kind of things that they were doing. They were looking at, like I said, what they call collexemes. So they were looking at various kinds of constructions, and they were looking at the words, in this case here it's noun phrases that were that could appear in that construction, and they also were looking at verbs that could appear in these other ones. We'll look at only 2 of these because this has taken off a long time, but we'll look at the waiting to happen. And so what they did was they used the following 4 data points for all of those little studies they did in this one article. So they looked at the frequency of that particular lexeme in that construction, then they looked at the frequency of all other lexemes in the construction, and then the frequency of the collexeme in all other constructions, and then the frequency of all other lexemes in all other constructions. So this is, the typical Fisher test, where you have like this table of 4 values that you put as input for the Fisher test. Problem here, though, is that the only real observed data here actually is the bold-faced data that comes directly from the corpus. All this other data is supplied via subtraction from totals, and probably the most problematic of that is this one, what we call the D value, the D cell value, which depends on a calculation of the frequency of all constructions in the corpus. And they were looking at the BNC, and basically what they did was they looked at how many verb tags there were in the BNC, which was like 10 million and something or other. So you had like a Fisher test table that had this one, which might have 10 or 100, and this one might have, 1,000 or something, and this might be a couple thousand, and this was 10 million. Remember that the Fisher test was designed for very small numbers and very small differences. If we go back to the history of the Fisher test, this was actually originally designed because there was a British woman, who claimed that she could tell the difference just by tasting a tea, whether the tea was poured first or the milk was poured first. And so she was blindfolded, and she was given a random sample of eight teas to taste. And she actually correctly identified out of these 8, and then Fisher developed this test to prove that this wasn't an accident, that this lady really could tell whether the tea was poured first or the milk was poured first. But we're talking about, she was given 8, teas to test. And here we've got something where we've got, maybe 8 items in one of our, in cell A, but 10 million in cell D. So this is not what the Fisher test was designed for. And also Fisher test was not designed to be a measure. But so here's what they did was they looked at like various noun phrases that could go in whoop, waiting to happen. So an accident waiting to happen, an event waiting to happen, et cetera, et cetera. And they got a p-value of, e to the minus 34 for accident, but of only 2 for event. And so this one was considered to be vastly more attractive than this word. But of course, their overall frequencies are very different too, and it's hard when I've shown this kind of data to statisticians. They find it kind of weird to use a p-value as a measure. And maybe we're going to skip over the ditransitive, since we already talked a little bit about some ditransitive. But, and I'm maybe going to skip a little bit to this, but what's wrong here is that the Fisher test was designed for small numbers, all on approximately the same order of magnitude, not going from like 3 to maybe 10 million. This D cell is really not an exact number. And note that the C value is dependent on the D because you get it by subtraction from D. And it's many orders of magnitude greater than the A and B values, which are between like usually 1 and 1,000. And the p-value for a Fisher test is not technically a measure. For many of the collexemes, there was only one example of its use in the given construction, and Stefanovic in Greece did a p-value measurement, if it is a measurement, with it anyhow. So there's been a lot of criticism from Bybee and, as I said, Schmidt and Kuchenhoff, and there's more debate on this coming out in a forthcoming issue of our journal. So that's still rather controversial. So nothing wrong with the Fisher test, but one should think carefully about where it comes from and how it's most appropriately applied. Okay, another type of test that you might have heard of is ANOVA. It sounds like something that comes from outer space, but actually this is just a abbreviation for analysis of variance. Analysis of variance, that's ANOVA. And when do you use ANOVA? So this is when you have like two sets of scores, basically, and one set of scores was achieved under one set of conditions, and another set of scores was achieved in another set of conditions. And you want to know whether they're different or whether they're the same. And I'm going to show you, in a minute, I'm going to show you an example of how Russians perceive marginal factative verbs like aseriosnits and uvkusnits. And if you tell me that those aren't verbs, then you're sort of right, because they're actually marginal verbs that are very, very, very rare. And what's ANOVA? Basically, if you had like two groups of students, one who took a test, and one group of students got extra help from the professor, and the other group of students didn't get extra help from the professor, and you wanted to know whether the professor was any good and that their help was helpful, then you would want to know whether or not the scores from the kids that got help were actually better than the scores from the kids who didn't get help. But of course, they got a range of scores, and those scores probably overlap, right? So what you want to figure out is whether the variation within the group is greater or lesser than the variation between the groups. And so you have, what ANOVA is, it gives you an F score, or an F value, that's the between groups variance divided by the within groups variance, and you also get a P value to measure like how surprised you should be, I mean how important it is that there was this difference here. And, you know, pretty obvious, if the, given that formula there, that if the F value is less than 1, then the within groups value variance has overwhelmed the between groups, and we can't see any effect. But if it's greater than 1, then we are seeing an effect. And this can also handle multiple variables. But here I'm going to give you this example that we did with Anya and Dresen, with these Russian factative verbs. So we have a bunch of factative verbs in Russian that we can form from adjectives using various prefixes. The two prefixes that are used the most are o and u. And we have standard verbs that everybody will agree exist, like obъяснить and ускорить. And then we have marginal words that probably a lot of you don't like so much, like aseriosnits and uvkusnits, but they're perfectly understandable. They're even understandable to me. And then we have verbs that I hope nobody will like or understand, like asurids and usagnits, which are nonce verbs, right? And what we did was we took 10 verbs with each prefix for each of these groups. Each of these three groups, so we had 60 groups, and we had an experiment, and there were fillers and pseudo-randomized order, et cetera, et cetera. And they were supposed to score them according to a 5-point scale that was supposed to remind them of how grades are usually assigned in Russia, so this should be easy to do. We also looked at age, but it turned out not to be a factor, because once you have people old enough so that they can read sentences from the Russian National Corpus, they're too old. They're already too old to show a difference from adults. Yeah. So so we did. Here's the distribution. So this was the highest score that something that a verb could get, and this, you know, with the lowest score was 0, of course. And we see this distribution. The standard verbs were pretty much scoring at ceiling. But what I found really strange was that the marginal verbs looked a lot more like the nonce verbs, and actually overlapped in their distribution with the nonce verbs. I thought that was pretty strange, because they have obvious meanings and are just as transparent. I mean, to me, aseriosnits is just as transparent as obъяснить. So why would there be such a big difference here? But they were very different, and so here are the little statistical descriptions of these distributions, and we did an overall ANOVA, and basically there's a very strong difference here, and we had a very high F value. We also did t-tests comparing individually between the standard and marginal and between marginal and nonce. And all of those are also significant differences, although obviously the first difference is much, much greater. So that's an example of ANOVA. Here's another example of how ANOVA has been used by linguists. Here's Ava Dombrovska, who's looking at long-distance dependencies. Basically what she was showing is that there is an effect of prototypicality here. So basically her idea with long-distance dependencies is that it's not so much about syntax as about chunks, because you have chunks like what do you think that looks like a long-distance dependency, but really it's kind of used as a prefix chunk. I don't have a lot of time to go into this because we're beginning to run a little bit out of time. So now I'm going to go to correlation. What's correlation about? Correlation is when you have a group of items, each of which has two different numerical values. Just like all the people in this room, you all have a height and a weight value. And then we could do a correlation to see if our heights and weights are correlated, if taller people weigh more. And I looked at this in the previous talk where we looked at the use of the possessive suffix, for example. So some interesting things about correlation. So +1 is a perfect positive correlation. I'll show you what that looks like. 0 is no correlation, and -1 is a perfect negative correlation. Caveats is that it assumes a linear relationship, and also correlation does not imply causation. It just says that there's a relationship. It doesn't say that one is causing the other. So here's a strong positive correlation. Here's a strong negative correlation where the dots basically, they line up along these lines. And here's an example of really no correlation. Oops, sorry. And then here's this caveat about linearity. These four sets of data all give you exactly the same regression line and the same correlation value. They are all identical. This is why you should always look at the scatter plot, because here we have a real legitimate positive correlation. Here we have a correlation, but the correlation is not linear, it's curvilinear. Here, in both of these two, we have one outlier that's completely changing the picture. Yeah? And so one should probably suspect this piece of data and take a look at it and analyze these in rather different ways. So I already showed you this before, for the people who were in the previous hour. Basically, this NPX possessive construction is dying out in North Sami. It's being replaced by this analytic construction, and then we asked whether this is related to frequency, and basically, it's not. We've got a very relatively flat line, and it's not going in the direction that we would predict it should be going. Other ways in which correlation has also been used to look at long-distance dependencies. We're kind of running short on time here, so I'm not going to say too much more about this. But here we have a bunch of verbs that were measured for two different types of tests, and we have a very close negative correlation between those two types of syntactic tests. Regression is built upon correlation, and this is really useful when you have found or suspect you might find a relationship between a dependent variable and an independent variable, but you have to take into account some other variables too. And here's some work that was done with Svetlana Sokolova and Olga Yashevskaya, although Sveta is the person who collected most of this data. And we were looking at the distribution of the theme object construction like gruzit sienom na tiliegu as opposed to the goal object construction like gruzit tiliegu sienom. And we were looking at three sets of variables. We were really interested in the first one, the verb, so whether the prefixes made a difference. But we needed to take into account also participle and reduced, which also had some influence on that. And so we did a logistic regression analysis of 1,920 sentences from the Russian National Corpus, and we arrived at an optimal model here of predicting the construction based on a verb and reduced and participle, and that we also found an interaction between verb and participle. And I think I'm not going to go too much more into this, except for that there was. Here we go. We can see that we have very significant results for all of these items here, which involves the verb and the reduced and participle. But you have to be able to interpret the intercept, and I'm not going to have time to go into that. But we found that the verb was by far also the most important value. I'm going to also, in the interest of time, I'm going to I'm going to show you the cart analysis of this one, yeah, and then I'm going to skip another one. So here's the same data with the cart analysis, where we also looked at this грузить сено на телегу and грузить телегу сеном. And here we have the distribution of the data, and here we see that verb is the most important variable. We see por behaves very different from na and za, and then we actually also separate out na and za later on. Although participle is also doing some job on this, and reduced is also doing some job in sorting out this data. But the verb is by far the most important or the strongest variable here, and we are actually able to measure this with this cart analysis. And here's what I'm going to skip over this other regression, because I wanted to talk to you also about mixed effects and also a little bit about clustering. So mixed effects. So say we have a regression type of question, but then we have also personal preferences that are into the mix. So say we did a test here on how fast people in this room responded to standard words as opposed to nonce words in Russian. The problem is that Olga might just be much faster in responding to everything than Garik is. Yeah.
No, it's just otherwise.
Or the other way around. Maybe it's the other way around. And that difference might overwhelm the difference between standard words and nonce words completely, because Olga and Garik are so different to begin with. So we have to factor out the difference between Olga and Garik before we can figure out anything else. So, and that's what we do with mixed effects, is that we can have both fixed effects and random effects, which is individual preferences. And individual preferences aren't just about human beings, they're also about verbs and concepts and such. And here we have an example, some examples of random variables. So there's subjects in an experiment, authors in a corpus, they can have personal preferences. Verbs in a language can have different individual behaviors. And here's an example of how some people have used a mixed effect model. These are some researchers in Leuven who love to look at varieties of Netherlandic and Belgian Dutch, for example. But here they're looking at English loanwords in Dutch. And they looked at lots and lots of factors. We can't go into this too much, but they also had an independent variable as a random effect was the concept expressed, whether or not that had an effect. So they did a big, complicated analysis of this, and some interesting kind of things they found. For example, if the concept frequency, as the concept frequency went up, if the Anglicism was shorter than the Dutch word, if the English borrowing was shorter than the Dutch word, then it didn't really matter how frequent the concept was. But if the concept was very frequent, then it mattered. Then the Anglicism was not the shortest. So the Dutch was the shortest word. If there was if it was a frequent concept, then they preferred to use the Dutch word. So kind of interesting things going on here, and some other things about the vowels, I guess I won't go into this in the interest of time because we've got to give back the projector in 5 minutes. Okay, so cluster analysis, trying to figure out what kinds of things are grouped together. And there's various ways that you can do this. Basically, if you have a string of numbers, a vector of numbers associated with something, and then you can measure the distances between those vectors of numbers. And there's various mathematical ways to do this. There's multidimensional scaling and correspondence analysis and hierarchical cluster analysis. I did some hierarchical cluster analysis on some data that was actually gathered by Valery Solovyov at the University of Kazan. We were looking at nouns for happiness and sadness. Here I'm showing you the sadness. And you can see already that these items behave differently from each other. So we have pichal, toska, chandra, melancholia, and grust and ulinia. And we see that the chi-square shows that this is very significant, and we have a good effect size here. But the question is, which of these are more alike? And we can do a clustering analysis and find out that pichal and taskat behave very similar to each other, whereas grust and ulinia are really outliers. And that's actually fairly obvious. Also, if you look at the data, this thing here, here's ulinia, which seems to just like v, I guess is something that you fall into ulinia, whereas grust is something that you do as an accompaniment. There's a grust here. So that's maybe not so surprising. Here's another example we did of a correspondence analysis. There's a controversy over whether Old Church Slavonic already had verbs that were perfective and imperfective. And what we did was we looked at the grammatical profiles of them and asked the correspondence analysis to just sort them out and say, put them into 2 piles. And this is some work I did together with Hanna Eckhoff. So we looked at the grammatical profiles of verbs like tvoriti and gianti. Here you see their grammatical profiles, and we said, okay, measure these vectors and figure the distances between them, and see what happens. And here's what we got. I know you can't see those; they're really little, but what it does is it calculates a multidimensional space that that accounts for various amounts of the variance in the data. And factor 1 is always the most important factor, and it sorts all the verbs into 2 values, which would be minus and plus here. And this accounts for about 40% of the day. So we have verbs on this side of that line and verbs on that side of that line. So we have verbs with negative factor 1 values, and these were 96% equivalent to Antonin Dostal's listing of Old Church Slavonic verbs as imperfectives. And we have verbs with a positive factor 1 values, and these look very much like his perfective verbs. So it was kind of, this is kind of one of those moments when you look at the graph and you jump up and down and say, wow, this is kind of exciting, because it seems that there is indeed evidence for that. So that's kind of my little quick summary of some ways to use statistics in cognitive linguistics. I hope that was useful, and I hope that all of you will consider doing some statistical studies, and when you do, that you'll share your data with us by putting it up on Trolling, so that everybody can compare and also learn from the ways in which you have analyzed your data. So thank you so much.